Сегодня у нас первая лекция цикла лекций, состоящего из двух лекций, профессора Бейсенса из Высшей школы технической физики и химии Парижа. Это знаменитая школа, я уже рассказывала, в которой работали долгое время 5 нобелевских лауреатов, включая химика Шарпака, и Ладживен был много лет директором этой школы, и, наконец, последним нобелевским лауреатом, работавшим тоже директором этой школы, Фойдежен. Значит, эти две лекции, они, в общем-то, несколько близкие по тематике. Вот эта сегодняшняя лекция касается краевых эффектов в конденсации капель. Как вы видите на слайде, на первом слайде, ну, здесь профессор Бейсенс нам об этом расскажет и ответит на наши вопросы. Так что задавайте вопросы. Профессор Бейсенс, он специалист в области критических явлений, скейлинга и, в общем, фазовых переходов в жидкость приблизительно динамической критической точки. Он имеет несколько монографий в этой области. Одну из них они как раз только что закончили с другим ученым французским, который вместе с ним получил гран-при Французской академии наук за исследование в области околокритических систем близительно динамической критической точки.
Thank you, Даниэль. Спасибо большое. So I will speak of a problem that perhaps you didn't notice. That is that deals with phase transition basically, and phase transition from vapor to liquid, and on a surface. So that's a problem which is in fact connected to dew. Dew, you know what is condensation outside. So that's an atmospheric problem, that an atmospheric physics that I don't tell. But also that's a phase transition, as I said, and also wetting phenomena. And as you have seen, the basic goal of this study, the goal behind, it is to get water. That is to get water from the air in a passive way, and especially if in places where water is rare, is difficult to get. So this is the affiliation. It's the ESPCI Paris, where I'm currently working. This is my institute, the Commissariat à l'énergie atomique, and this is the organization for dew utilization, OPUR. I'm the president. So this work has been done with people from ESPCI, Anne Mondruel, from the University of Nice, Riviera, that's a good place, Marie-Gabrielle Médici, and Laurent Royot from University Paris Diderot, Paris 7. So the motivation, as I told you, it is to get more water from dew. And especially the problem that limits dew, you know, when dew is forming, it makes tiny droplets. And to get them, you incline the surface, but when the droplets are too small, they are stuck, they are pinned, so they don't flow. So our goal it is to collect these very small droplets. And there was people with women interact in Korea. You know, that's in a Korean name. And they look at the collection of the condensation of droplets on a vertical surface and to see what is the best surface to make the droplets to flow. And they look at super hydrophobic, that is small pillars, hydrophobic, regular one, that is like this, hydrophilic, so it makes a film, and eventually the film makes a big drop at the end. This is a very big drop. That is pint, anyway. And also super hydrophilic and hydrophobic, that is pillars that are hydrophobic with a head that is hydrophilic. And you see the scale, that's not very large, that's only, say, 10 millimeters, so the square is about 30 millimeter over 30 millimeter. And in fact, in current life, we need very big panels, and 1 meter, 10 meters, 100 meters. And so that's difficult. Anyway, you see that still the small drop, they remain thin, even though here there are flows. So, in fact, the study that I will discuss here is based on nature and observation. So I was really amazed, surprised that if you look at the windshield of a car, that's the André car, it doesn't work, so it collects dew, you know. And so you see that the drops, they don't flow. You see that drop that has detached and make an avalanche. So, and these drops, I was thinking that they should detach randomly on the surface. That's not true. They all detach from this or there, from the side. So this means that since they detach from the side, this means that they grow faster on the side. And why do they grow faster? That's the object of the lecture. So now if you look also, that's in the lab, in my lab, so we took a piece of aluminum, and behind there is a peltier, so you cool it, and you see the droplets forming, and you see that the droplets are indeed larger on the side, that's in the middle, that's why they detach from the side. So this should, okay, so that's a moving principle. It is accelerated 10 times, or more than 10 times, 100 times, because that's hours of experiment. So again, and you see that the drops, they are larger here and there, and so they detach sooner. And so that's very interesting, because naturally, the fact that the drops are larger on the side makes them, when they float, they are like wipers. That is, they wipe out and they collect the other. It's like, you know, on the car, the windshield, it's the same as you were scraping the drops. So the drop itself here scraps the other drops. So that's very impressively efficient. So this is a natural way to collect more water. Now we study why do the drops grow larger on the edge. Why do they grow larger on the discontinuities? So we consider this experiment. So that's a box, plexiglass chamber. Inside we have humidifier. With a fan, we don't put the fan. We measure the hygrometry and temperature of the box, so that's a big box. Huh? We put the substrate under study on a Peltier element. A Peltier element, you know, the Peltier element, it heats on one side and cools the other side when you send electric current. And you look with the camera above and you record on the computer. So that's why you can see. So this is a block which is 10 millimeter high. It's cooled from below, and it is coated with PVC, 0.1 millimeter thickness. And that's the side, 17 millimeter. And you see that in the center, the drops are smaller than on the edge. And especially in the corner, they are larger. Now, that's on another scale. That's the same with silicium wafer under microscope. And here also, that's 1 millimeter scale. You see these drops are larger than the drops in the middle, and the corner drop is still larger than the drop in the edge. Now, we made another kind of discontinuity. So this one, this was geometrical discontinuity. Now we make a thermal discontinuity. That is, in this block, there is a hole. It is coated also with PVC. And since this PVC is not cooled, there is no condensation. And you see, when there is no condensation due to thermal effects, the drops, they grow larger. That's also the same here. That's two blocks with a polypropylene now that is 20 micron thickness here. So here that's not cooled. That's not cooled. No drops. And you see that on the edge, the thermal edge, what we call the thermal edge, and geometrical edge, the drops they grow larger. On the corner they grow larger, etc. So you see, when there is no, so now I think you understand what's going on. Here the drops, they get moisture from above, and they compete for this moisture. They have to compete between them. But near the edge, they don't have this competition, and they can collect moisture from the side. And in the corner, they can collect moisture from this side, that side, and the other side from three sides. So in fact, the role of edges, that makes the drop collect more moisture, more humidity. So now we will try to quantify this effect. And here it is. So for the experiment, we consider aluminum block, 2 millimeter thickness, with, so there are edges here, corner, but we make a groove here, something hollow, and here we make a scratch. So that's what we get. So we get the drops here and there. And so here you see that you can measure the drops in the central area, in the edge area here. On the scratch, you see there is some alignment. That's for the nucleation of drops. The center of the groove here, and the edge above, out, and the edge, the groove inside, edge, and the groove out, edge. So inside you can measure it. And you see that if you compare the central, you see that the edge, the drops on the edge are larger than the central. The drops in the middle of the groove, they are nearly the same as the central, but somewhat smaller. The drops at the edge, out of the groove, they are larger, and inner, they are much smaller. And on the scratch, they are not so different from the central region. So, and the corner, of course. So now we can measure the radius of the drop with respect to time, and we get the growth laws. And for the growth laws, I have to make some theory about it. So I apologize, but this is some mathematics and some physics. So the growth of a drop starts from nucleation. And nucleation is a phase transition where with the molecules of water, that's vapor, and you are at a temperature and pressure where liquid is favored. To favor liquid, you need to overcome the energy barrier of the interface. And so this means that you need a large supersaturation for a drop with a critical radius to form. So I won't tell too much because that's a field in itself. But this means that when you have a surface with scratches or holes, it favors nucleation. So the nucleation starts on defects where the nucleation barrier, due to the formation of the interface of the drop, is lower. Now, once the drop has formed, it grows. And it grows at the expense of the water molecules outside. And that means that you have in the air around, in the humid air, you have the diffusion of water molecules, and when they hit the drop, they will be incorporated. So a concentration gradient will form. First, I will just but when the concentration gradient forms, you need to know where is the saturation at infinite, what is the boundary layer. Note that on the surface, which is cooled, you have a flow. And you have at least, you can have a forced flow, that's a kind of wind, but you have also natural convection. And so I would like to address the boundary layer of this convection. So what you have the natural convection, so you have a boundary layer which is 0 on the surface and 0 far from the surface. So that's the velocity here. And the size of this boundary layer is related to the Grashof number. The Grashof number, that's gravity, acceleration. Beta is the thermal expansion coefficient at constant pressure. Delta T is the temperature difference between the surface of the plate and the air temperature. L, that's the typical size of the plate. And nu, that's the kinematic viscosity. And so if you say that with this number, that's Earth, that's humid air, that's air, that's on the order of centimeter, nu, that's the humid air viscosity, and delta T, that's on the order, or say a few degrees, 5 degrees for dew formation, but 9 degrees for this experiment. And so you get a Grashof number on the order of 13,000. And now you can express, but that's a calculation which is out of the scope of my presentation. The size of this boundary layer is related to the size of L by Grashof at the power minus 1/5. So that's with this number, you get something, an L of the order of centimeters, you get something like 4 millimeters. And this means that now, if you assume that the profile of the velocity here and there is parabolic, that's a Poiseuille laminar flow, you can determine the layer where diffusion of water molecules will be more efficient than convection. And you know that for that you have to calculate the Peclet number, where you have the velocity of air. Here we know the velocity, the maximum, that's on the order of 3 centimeters per second. That's the relationship with delta and all the other parameters, divided by the mutual diffusion coefficient of water molecules into air. So when Peclet is lower than 1, this means that diffusion is favored. That's exactly what we want. When diffusion is favored, it means that you have no more effect of convection. So you can ignore the air velocity. And so here we calculate the thickness of the mass diffusion boundary layer, zeta. It's when Peclet number is equal to 1. And so typically with this profile, and you get zeta on the order of 2 millimeters. This means that when the water molecules will reach the drops, at 2 millimeters here, you have a constant concentration of water molecules. So a gradient will form from this value to the drop. And in this gradient, the drops will grow. So now the next step, it is to estimate the gradient. Okay, so you consider the drop on the surface. Here you have the boundary layer. And here you see you have the diffusion of molecules. When they hit the drop, they are incorporated. So that's the saturation pressure or concentration at the surface of the drops. And here on the hydronic boundary layer, you have the concentration at infinity or the vapor pressure at infinity, which correspond to the air temperature and the relative humidity of the air. So you know that the probability of water molecules to be incorporated is larger here than there. This means that the concentration of water molecules here will be less than there. So a concentration gradient forms. And there is a symmetry, a spherical symmetry, to solve this problem. Now, to solve this problem, you just express that the growth of the drop is due to the diffusion of molecules and its incorporation. So you have to solve this very simple equation. It looks simple, but to solve it is not simple. So at any place here, you have the evolution of the concentration of water molecules, which corresponds to the diffusion by this diffusion coefficient. And here, that's the Laplacian of the concentration. So that's a difficult problem because it is called to solve this problem. It's a Stefan problem because there is a moving boundary condition. Anyway, you can express the flux that hits the drops is connected to the diffusion coefficient and the gradient at the drop surface. And so the volume evolution, that's the integral on the surface of the drop of this flux. So that's only calculation, simple calculation. Now the problem is that, as I told you, this is a very difficult problem, that's a moving boundary condition, that can be solved only in specific cases. And so, to simplify it, we suppose the quasi-static approximation, that is, during the growth, the gradient doesn't vary very much, so dN over dt is equal to 0. There is no time evolution of the gradient. So the drop grows, but the gradient doesn't evolve. And so you have to solve a more simple equation, which is the Laplacian of concentration is equal to 0. So that's only geometric. And so if you express in this geometry the Laplacian, you can solve this equation and you get something which is well known, which is an hyperbolic, this is R, hyperbolic concentration profile. So you see that small r is equal to large R, you get n equal to ns at the surface of the drop. When r tends to infinite, you get n infinite. That's further on the hydrodynamic boundary layer. So now, if you want to see the growth law, so you express dv over dt at the integral of g, so you have dn over dr, so you can calculate this parameter, this derivative, by derivating this equation. And so you get this equation of evolution, that's dv over dt, and that's d12 and dn over dr. Yeah. And that's the surface of the drop. You integrate over the surface, so you have the surface r squared. And so you get something which is well known, which is the radius is growing at time at the power 1/2, root squared of time, with a prefactor t1, the growth rate, which is, so the growth rate that's the inverse of t1, is proportional to d12 and the difference in saturation pressure between the air and the drops, that is temperature below. You can also express in terms of vapor pressure. Okay, so till now everything is simple. That's something which is relatively well known. So I give a course at the university where I explain to the student all this stuff. Now, have you seen the drops? They are close together. You have seen they're close together. In fact, the concentration profile of the drops overlap. And so in average, the concentration profile is not hemispherical, but it is rather directed perpendicular to the surface. So we can make a film approximation. So it's like if we had a film growing from the outer surface. And so we can say that all the liquid that is in the drops is spread to make the film. And so the drops, they are in average separated by distance d, average d. So we can say that the height of the film, that's the volume of the drops divided by d squared. So I remove the factor pi, etc., and that's proportional. And so Vi is proportional at the radius of the power 3 divided by d squared. Okay? Now, to solve the equation for the film, we said that delta n, which is the second, there is only one variable, that's z. So the gradient that's d2n over dz2 is equal to 0. That's easy to integrate. If you integrate one time, that's a constant. And two times, that's a linear profile. So here, that's a linear profile. You see that when z is equal, so that's z minus h, because you have to take the gradient from h. When z is equal to h, you have n is equal to ns. And when now z, you cannot send it to infinite, but you put at the boundary layer, zeta. When z minus h is equal to zeta, you get n infinite. Okay? And so now you can express dh over dt from this equation, and you get dh over dt, which is, it is related to the derivative versus z. So you get n infinite minus ns over zeta, and you get a linear graph law. So the volume of the film or the droplets, that's the same, grows as time. So this means that the radius grows as time power 1/3. You see, that's quite different. One single drops, the radius grows as root square of time. When you have a lot of drops, each drop grows as t at the power 1/3. And now the prefactor, the growth rate, that's simply the diffusion constant, supersaturation, and zeta, the boundary layer thickness. Now you understand why I was discussing the boundary layer thickness before. Now, the drops, they grow, but they touch each other, so they coalesce. Here, that's the drops growing on a slide, on a flat surface, and you see that they grow, and eventually they touch, and when they touch, they I would say, the new surface is lower than the surface of the two previous ones. So when they coalesce, they remove some liquid from the surface. They grow in a third dimension. And you see, they look to have nearly the same radius, but with the growth, the radius grows and rescale the growth. Okay, so I will go a little bit further. So now that's a very key phenomenon. That's growth and coalescence. So you have two drops that makes a new drops. That's the two parents, and that's the daughter. So you have the two drops, same radius, that's simple, same volume, and the volume of each is 2 pi r3 divided by 3. Simple. Now the fusion, and that's a new radius. Is obtained by telling that the volume of this drop is the sum of these two drops. And so you say that's 2 times 2 pi over r3 divided by 3, and you say that's r prime, okay, and you get r prime equal r to the power 2 1/3. And that's easy calculation. So this is equal to 2 pi r prime 3 over 3. And so the surface coverage now, here we have 2 times pi r squared. Now we have pi r prime squared, which is pi r squared by 2 to the power 2/3. And you see that 2 to the power 2/3 is less than 2. So this means that the surface covered by the drop on the substrate is less. So now the substrate is drier than before. And so that's the key of the rescaling and the growth. This is constant because you see that each drops, they go and wet the surface, but by growing, it hits another one, so it gives less surface. So the surface coverage increases, decreases, increases, decreases, but in average it remains constant. And that's why the growth is self-similar in time. Well, I don't go further, but this is the diameter 2r of the drops in a log-log scale, that's time. You see, if you put a dye on a drop, it grows, coalescence, growth, etc. So if you look only at the growth between each coalescence, you get 1/3, as expected, as I told you. That's the film approximation. And coalescence speed up the growth, and you get 1. So this can be explained by the following way. If you look, say, now the substrate, the radius Ri, contact angle theta, and the volume is f of theta Ri at the power 3. So now you can express the average radius of the pattern by the sum of the radius of the power 3 divided by the power 2. So you have seen that epsilon square should be a constant. That is, sigma of Ri squared by pi divided by St should be a constant. And the volume of all the condensed volume, that's the sum of the volume, that's f of theta, by summing over the sum of volume, that's f of theta, by the sum of R3. And so you see something interesting, because here you get something constant, proportional to the surface here, and here you get something which is proportional to total volume. And the total volume, we know by the film approximation, it grows with time. So this means that the average radius is proportional to the volume, which is a very paradoxical result. The total volume. And grows as time. So the average radius will grow as time, will be linear in time. And with the growth rate, which is the growth rate as we have seen before, that is supersaturation divided by the boundary layer thickness and the diffusion constant of water molecules in the air. Okay, now we have all the tools to understand the growth on the edges and in the center. So sorry that these tools, sometimes they are not so light. So now just to, well, we can say that all these results here can be generalized. That is, if you have drops of dimensionality large d that grows on a substrate of smaller dimensionality, you will get the average growth will be with power gamma, and gamma will be 1 over droplet dimensionality minus substrate dimensionality. If you're interested, I can make the demonstration later, but I think it's not necessary. And so, okay. Now, if you look, for instance, at 3D droplets on 1D and 2D substrate, why I'm doing so? Because on one edge, it's like 1D because the drops can be aligned. Or if you put a scratch, you have, it's like 1D, so 3D droplets on one. So this is inspired by nature. So you get an iris leaf, and you condense the iris leaf. And you see that the drops, they nucleate on the structure of the leaf, and they coalesce mainly, they fusion mainly in one direction. So that's a 1D substrate. And the drops are 3D. And so you look now at the growth laws, so that the mean radius, time, and you see that if you look initially when there are only a few drops, you get a 1/3 growth law. Now if you look on the line, you get 1/2 growth law. And now when the drops they are much larger than the size of the structure, you get as if it were a plane, and you get the 1 growth law. And individual growth that's 1 over dd, of course, because the volume is proportional to time, and the volume of dd dimensional drops, that's proportional to r at the power of dd. So that's easy. Now the coalescent there is scale, and so on a line you have 3 minus 1, which makes a 1/2 graph law. Here it is. And on a plane, you have 3 minus 2, it makes a 1 graph law. Okay, now we go back to the edge effect. So that's brass cube plus PVC, and we look at the average diameter of the drops on the here in the middle, on the edge, and on the corner. And you see, so this was the experimental condition, 22 Celsius, 44% humidity, and the substrate was at 4.8 Celsius. That's the radius and the time. That's linear. You see that there is a linear growth law. And you see that that's the central area. And you see that the edge is growing faster, the slope is larger, and the corner is even faster. So, same exponent. Also now, you can tell me that why there is a linear growth law on the edge and the corner. I can make also a demonstration. That's mainly because here, you know, the linear growth law comes from the film approximation. And the film comes from the fact that you have superposition of the gradient around the drop. Here also you have superposition of gradient and also in the corner. So as long as you have superposition, as long as the drops are close enough so that the main gradient is directed perpendicular, you have the film approximation and the linear growth law. So here, for instance, you see that's the growth rate in millimeter per minute, and if you rescale the corner to the plate bulk and the edge, you get a factor of 4 with respect to the center, and on the edge a factor of 2.5. That's not a small factor. This means that the drops on the corner, they draw 4 times faster. Now, for the aluminum plate, you see that's more complicated. You have the central area, you have the corner and the edge, corner and edge, and you have the groove. You have the groove upper, that is on this side, which grow faster than central, and the groove lower grow, I didn't put it, but it's smaller, it's below. So that's the number. The groove in the central area is less than in that central place, and the corner, that's nearly 5 times the central area. Now, you can also limit growth by limiting the cooling influx. For instance, if you remember, there was the tape on the hole, there was no condensation. But now you can make something in between by taking a plexiglass. Plexiglass, that's polymethyl acrylate, and the conductivity is much less than aluminum. So, for instance, the ratio of PMMA versus metal, it's nearly 1,000 times less. So this means that even though you can cool the surface of plexiglass, you will not have enough flux to have a very fast growth. And you will see that in this case, there is no edge effect anymore. That is, on the edge, on the corner, that's the same as in the middle. That's because now the limiting heat flux, that's not the gradient, that's not the moisture coming from the side, but that's the cooling heat flux. And here, instead, in the groove, instead of having a growth rate smaller, we have a larger growth rate. Why? Because here, the cooling heat flux is larger because the substrate is thinner. And you see here the substrate is 2 times thinner than there, so the growth rate here is here, that's central groove here, is 2 times faster than in the central area here. So that's just upside down, that's the edge effect with metals. The plexiglass, the low conductivity material limits the growth. Now, in order to fit this data, we made a 2-dimensional numerical simulation. As you have seen, the growth is due to the Laplacian, to solve a Laplacian. So we solve this Laplacian in 2 dimensions. So you have this equation, delta n equal to 0, in stationary and 2-dimensional. So we use finite element method with periodic boundary conditions, something which is very classical. The drops, they are uniformly distributed on the substrate, and the border corresponds to the symmetry. So you have the gradient is 0 on the substrate wall and the symmetries. And the surface where the vapor concentration is known, we have the drops where the concentration is 1. And the boundary layer where it is 2, and that's in reduced units. Okay, so now we are in the coalescence-driven stage, and so these are the drops. They are separated by 200 microns, by 250 microns, and their diameter is 200 microns. So the surface coverage is about 50%. That's which is usually obtained. The boundary layer thickness, that's 1 millimeter. And here, that's the first simulation. So you have a corner with the drops, and you have the boundary layer here, so at 1 millimeter, here and there. And you see this corresponds to the current, to the flux. And you see that, first, that's interesting because the film approximation where the concentration gradient is perpendicular in average to the drops, that's really obtained. And now you see that here, these drops, they collect water from this layer and from that layer, so they grow faster. And you see that the gradient, that's the value of the gradient, the colors, is much larger here than in the central area. Now the drop growth rate can be expressed, as you remember, by the diffusion constant and the integral on the surface of the drops by the gradient at the surface, the concentration gradient. And so you can calculate it. You can calculate it here and there for each drop. So we will calculate it in 2 positions, this position and that position. And we measure something that on the order of 2. Now, another case, that's for the groove. So the groove, the substrate is like this with the groove, and that's the boundary layer. And you see here, of course, the growth will be slower because the prefactor, you remember, was inversely proportional to the boundary layer thickness. Here, the boundary layer thickness is 2 times larger. So the gradient is 2 times smaller. And you see that when you compare 0 to 2, we have a factor 1.6. And when we compare to inside, that's upside down. Here, that's nearly 2 times lower than in the central area. Now we have the thermal discontinuity. So we just consider drops on this part and not on that part. And you see that the same. You have a gradient which is perpendicular substrate. And here you have this drop collect moisture from this boundary layer, but also from that side, even though there is no boundary layer. And you see the gradient is much larger. Here the drop, they are in competition to have the gradient directed perpendicular to the substrate. Here there is no more competition. So that's why it collects more moisture. And so now the ratio, that's on the order of 2.6. Now we can compare with the experiment. And so, as I told you, the volume, total volume, is proportional to the average radius. And so that's what we get. So that's here, that's the temperature of air the surface temperature, the relative humidity of air, and this corresponds to the supersaturation in kilopascal. And in order, since there are different conditions, what we will see, we will compare each geometrical discontinuity to the central part, that is M. So we start with corner, that's corner. So it receives moisture from 3 different directions. That's different substrate here. We don't have simulation because the simulation is 2D. But now that's on the edge, we have a simulation. And you see that simulation gives nearly something of 2. And we have something which is not far from 2, a little bit more. But that's normal, that's 2-dimensional. Now we have the groove, up the groove, 1.6. We measure 1.6 for the simulation. We have the groove, central part of the groove, 0.86, 0.43. There is a difference because, you know, we assume that in the simulation that the boundary layer has a constant thickness, but here you see it shows that due to the hydrodynamics, it should go a little bit inside. Now that inside the groove, close to the groove, we get 0.5. Here, that's for the same reason, that's 0.072. So that doesn't work very well. And that's the thermal boundary layer. That's also the same order of magnitude, 2.2, 2.64. Now, if you compare something with the thermal conduction, that is when that's the heat conduction that limits growth, you can compare this value, that is, you compare the value inside to the value outside, and you get 1.7 exponentially. Of course, you get 2 because the thickness here is 2 times thinner. Now, the problem that we can ask it is when you have, I was discussing the mass diffusion boundary layer. But now also, when you cool, you have a thermal boundary layer. So it means that if you want to have a growth which is faster, you have to lower the boundary layer. But at the same time, if you lower the boundary layer, you increase the heat exchange. So what you have to compare the thermal boundary layer to the mass diffusion boundary layer. But by chance, the thermal diffusion coefficient of air is nearly the same as the mutual diffusion coefficient of water into air. So this means that the thermal boundary layer and the mass boundary layer is nearly the same. Well, that's interesting because this means that now if you want to increase the dew yield on the corner, on the edge, without removing too much heat, you can make further calculation and further investigation. So that's to be done. So now it's interesting because when you have natural convection, the boundary layer thickness is not much delta T dependent. You remember it was proportional to the Grashof at the power 0.2. So it means when you go say from 2 degrees to 10 degrees, it varies only by 20%. So it means that for sample on the order of centimeter, this boundary layer is always on the order of millimeter for natural convection. For forced convection, that's different, of course. Now, of course, a compromise has to find between the diffusion boundary layer decrease that makes the gradient increase, and so the growth rate increase, and when you decrease the thermal boundary layer, you decrease the thermal one. So this means that the temperature difference decreases, and so the pressure gradient decreases. So you have to find a good compromise. That's something that we have to put in equation and to check. Now, field experiment to see whether this works or not. So these are dew condenser outside. One is an egg box. You see that's hollow. That hollow gives good rate because outside when you have the wind, the hollow structure prevents the wind from coming inside. So we have nearly velocity zero. And that's origami. Origami, that's with sharp end. And so that's in the field, that's the origami, and that's the egg box, and that's a flat surface at 30 degrees taken as a reference. So what I plotted here, that the reference, the yield of the reference, so that's liter per square meter per day, divided by per night. And that's the ratio of the origami and eggplant with respect to the plane. So of course, for the plane, this will be 1 reference. Now that's the egg plane, and you see this depends weekly on the rate. When the rate is large, we get nearly the same value. When the rate is low, we get somewhat more value. But there is no much edges. Here with the origami, we have sharp edges. And you see that here the yield is much increased, nearly 400 and 500%. Thanks to the study I showed you before. That's because the drop, they grow faster, they become larger on the edge, and so they detach sooner and act as a wiper. And of course, when the yield is large, there is not so much influence, but the yield is small, you see the difference. So now, I just go to the end of this lecture. So that's the movie, remember? There is the growth enhancement near the edge corners that can reach nearly 500%. This means that the drops detach sooner and act as wiper. They wipe out the smaller drop. So this could be, as you could see here, so this could be improved by allowing the drops above to detach still sooner. So to detach sooner, you have to decrease the hysteresis of the contact angle. Because what makes the drop to be pinned, that's a pinning, this can be expressed as hysteresis. So you can make, for instance, very soft Teflon or microstructure or super hydrophobic substrate at the top. This will help the drop to detach. But that's not easy because you have also the transition between the low hysteresis and regular surface. So perhaps the drop will remain pinned when they will hit the regular surface. Now, you can also cancel. Sometimes you want to cancel the edge effect. And as I told you, we can use low thermal conductivity. That's very efficient. Now, what can be done with natural dew with radiative cooling? You know that dew is cooled by radiation. That is, there's outer surface that emits infrared. This surface receives infrared from the atmosphere, from the sky. And during the night, this surface emits more infrared, so it cools down. So there is a thermal boundary layer, of course, related to this cooling. So that's the thermal boundary layer versus the mass diffusion boundary layer. And this needs more work to understand better. Now, you see there is an enhancement of growth near the very sharp end. So what is a very sharp end in nature? And that's cactus. So the idea to see whether cactus can be used as a very efficient way. And you know that we know that now that when drops, so that's a numerical simulation around the spine. So we are working on it. That's 3D. That's the flow. That's another flow. Now we are about to put the radiative cooling on it. So you see that on the cactus edge, when the drop is forming, on some cactus, when it is smooth enough, due to the gradient of contact angle, the drop that forms here goes at the bottom of the spine. So this is a very efficient way of collecting water also. So I'm studying this with the people from the London Royal Natural History Museum and people from MIT. So we had some outdoor experiments, and it seems to give really more efficient. So we measure the dew yield of cactus. So some cactus have good yield, some other have not. That's interesting. Okay, so thank you for your attention. That's the end.
Вопросы, пожалуйста.
So you have to ask question.
Yes, yes.
Yeah, your boss is here and...
Ну что, интересно же, какие у вас вопросы? Так, Сергей, у вас есть вопрос? Геннадий, у вас, наверное, есть вопрос. Наверное.
So you should find some compromise between boundary layer, thermal boundary layer thickness and mass.
Yes. Mass diffusion barrier.
So why you should?
Why?
Why you need this compromise?
Because you know, let's take the example of this study. So you cool a piece of metal, okay? So in fact you have a constant. In fact you cool by having a constant temperature of the piece of metal, okay? And so now you have this piece of metal that is cooled from below, constant temperature. You have constant temperature, and you have air. Air is at constant temperature and constant humidity. There is a constant concentration of water molecules in the air. Now you have as I tried to show you, the drops are nucleating and growing, and they grow faster if the thermal boundary, if the mass diffusion boundary layer is small. That is, what does it mean? It means that the gradient is limited to the boundary layer. So when the boundary layer is smaller, the gradient is larger. When the gradient is larger, so the gradient, that's the difference in concentration between air and saturation at the surface temperature divided by the boundary layer. Okay? So when this boundary is smaller, this gradient is larger and growth is faster. Now, the temperature, imagine before you have dropped, or between the drops if you want, before you have dropped, you cool the surface, and the temperature of the surface is due to a competition between the cooling flux, that the temperature of the surface minus the temperature below divided by the thickness of the materials, and the air, and there is another thermal boundary layer, which is the air temperature, the surface temperature, and the thickness of the ground layer. So this cooling flux is the same at equilibrium. The cooling flux is the same as the heating influx. And this, when you equal, this gives you the temperature of the surface. Now you understand that if the surface is cold, well, when you decrease the temperature of the surface, you increase the supersaturation. Maybe it means that the supersaturation, that's the difference in concentration. So if you get colder and colder, you get more dew. Do you understand? And if you are not very cold, the condensation is very, very small. So it means that the colder the surface and the faster the growth. But the colder the surface means that to have it cold, you need a large thermal boundary layer to remove the heating by air. So there is a competition between them. If you want to have a very low temperature, you need a very low convection above, a very large thermal boundary layer. But and this goes against mass diffusion. We can express the equation, but that's qualitative, you know. So this means that there is surely some optimization with the airflow, with the shape, etc. You can make
Yes, yes, you can take.
that's easier. Maybe there is a bigger one. Because I will make it. You know? So, this is T0 constant. This is the material with the thickness E. Okay? This is air with temperature TA. Okay? And this is the boundary layer. So this means that we call it, say, zeta. So at equilibrium without condensation, and that's okay, so that's the conductivity. You have, and that's the surface temperature. So you calculate the surface temperature by telling that. So that's TA minus TS divided by lambda R. That's lambda R. Is equal to Ts minus T0 divided by lambda. And this gives, so, okay, there is zeta. Okay. So this gives you the surface temperature. When you know zeta, E, lambda, so this gives you the surface temperature. Okay? Well, now, if you have condensation, so you have another boundary layer. So on the set side, this is zeta T, thermal. You have another one, which is zeta M for mass. By chance, they are nearly the same. Thank you very much. So we break now, we don't have to make it. And so now, you understand that TS, which, so now the growth will be proportional to the vapor pressure, so PS. So we say P infinity, see, and we'll have PS here. So P infinity, so we have minus PS divided by zeta M. Okay? So we have to make this as big as possible. So this means we will decrease zeta M. If we decrease zeta M, we increase the flux and we increase TS. So these are all these equations that you have to mix together. But that's even more complicated because I say that's PS, but that's not exactly PS. That's more, that's not so simple.
May I ask another one?
That's the basic of the reasoning, but it's really more complicated.
So, as you said, the goal of your study is to achieve the water, to have more water. But in another case, you know how reduce the age effect. So, for which situation we didn't need it? Why we should sometimes cancel this age effect?
Easy. No. I could say that if you have glasses, sometimes that's not very good to have like this. That's true that in principle the edge effects are beneficial. That's true. Maybe, but I didn't think where they are not beneficial. For instance, for the artist, you know, at the SPCI, I think you have seen it, huh?
Yes, yes.
We have two big windows. There is a museum where I'm working. So on the street there are big windows, and there are windows where we put different contact angles. So you see flowers made with a lot of tiny droplets. And that's bad to see that sometimes these droplets, they are wiped out. So it's better not to have. So that's an example. But that's strange because, you know, that's a very, this edge effect you can observe in nature, you can observe it in other places. So we sent the papers to a journal, and really, you couldn't see in the literature any study of these edge effects. That's very strange. People didn't notice it. Because in also industrial heat exchanger or condensation chambers, you should see it. But many people don't worry about it.
Есть еще вопросы? Вы можете по-русски задавать вопросы.
По-русски можно тогда? Вот у меня вопрос такой. Я, насколько понял, вы решаете прямую задачу, то есть описываете, моделируете образование капель и так далее. Возможно ли как-то управление, рассматривали ли задачу управления, обратную задачу, управления созданием капель с заданными характеристиками?
The question is, did you try to solve the problem of to create the drops with certain size?
What do you mean by creating? What do you mean by creating?
To form.
The drops, you know, that's the nucleation theory. Nucleation theory.
Теория зародыша образования.
Yeah. So just means that if you have the drops that can nucleate, they start from initial radius R star that depends on supersaturation, etc., and surface tension, and so we can create drops with R larger than R star. Practically speaking, if you have defects at the beginning, they are all the same size. This size, R star. So we can tune. So we can create drops of that size. But that's nanoscale. That is that usually that's 10, perhaps 50 nanometers. They are nearly all the same size. So that's just the beginning. So that's possible. That's, in a way, there are not many applications of these breadth figures. I've been invited in Japan in February, and I met a person there, and he said that from our work of breadth figures, they took a patent, and they're making honeycomb structure. Because when the drops, you can make the drops a lot like this, you know, very compact. And they made water drops in a matrix surface of polymer. They remove water, so after you have something which looks like honeycomb. You know, that's really something like this. I don't know exactly, but okay. That's more complicated. Okay. So that's really honeycomb, and that's Toshiba. No, these Japanese, they are really good for for making patents with anything.
Так, значит, вопросов не появилось. Подумайте до среды. В среду будет вторая лекция, и вы можете